Hello everyone. So continuing the DSA sheet, we are at the question called find the starting point of the list or the cycle, right? So this is the question, linked list cycle 2. The question states that given the head of the linked list, return the nodes where the cycle begins. If there is no cycle, return null. There is a cycle in a linked list if there is some node in the list that can be reached again continuously. And you already know, you have already read this thing in the first part, that is linked list cycle, right? So there are two parts. First question was detect if there is a cycle. Now second question is find the starting point, starting of this cycle, right? And in that question, I told you something, right? I told you that hey, it is not sure that when we use the slow, fast pointer approach, it is not sure that slow and fast will be at that position, basically will be at the starting position or not, right? Okay. Now, why is it so? The answer is that see, okay, yeah, we can discuss this when we are onto the proof of the part. But yeah, let's start with the solution, right? Let's start with the thinking of how we can solve this question. So basically, naive solution. If you remember, I told you in that video as well. If you haven't watched that video, please go and check it out. I told you that to keep the track of the starting point, you will have to use an extra space, right? Now, why do we use an extra space? See, if I am at someone's house, for example, right? If I am traversing in a colony, right? Or probably a society, right? I visited the house, then I visited a house, then again some other house, right? But if I come on the first house again, how am I sure that I visited this house or not? I should have kept a note of like if I visited this house or not, probably a tick mark or something, right? Okay. Now, if I don't have any, I don't have a, I am not saving it anywhere, or I'm not writing it down somewhere that hey, have I visited this house or not? I won't be able to, look through it that yeah, yes, I have visited this house or not. That is why we keep a track. That we have to keep a track, right? And how will we keep a track? We will use hashing. Now, why hashing? Why hashing? Because we have to keep a track. What can we use? We can use a map, we can use a set or whatever. I am going to personally use a set. Now, why is it so? Because I need to return the first index, right? Sorry, I need to return the I first node that I have visited again, right? So, you know, if this is the sorry, this is the list to 0 minus 4 and 0 again, right? Sorry, 2 again, right? If I have to return this 2, if I have to return this true, so I will check in the what do you call it, in the set that hey, I have visited this already, right? So what can I do? So if this is the head given to me, I can take a temporary here. We are not altering the head, obviously, right? So 2, so 3 is node with 3, right? It is saved. Now temp moves ahead. So N2, right? Temp moves here. Node with 0. Temp moves here. So node with value -4, right? As soon as I move here again, you will notice that I already have it here, So which is why I will return my return 2 because hey, it already exists in my hash node or in my hash. This node exists in my hashing or probably my set, right? Okay. So what is the time complexity, right? Let's discuss that first. We traversed all the nodes, correct? We traversed all the nodes one time, right? Cool. Is there any extra time that we are taking apart from traversing all the things? No, we are not, right? Obviously, we are saving everything. So we are either saving it or we are finding it. We are either adding or finding if that element exists. So that's 2 into log of n, depending upon what your set times is. I mean, what is the time complexity it takes to, add and find the things. This is something that you will have to see, right? And it should be multiplied because we are doing it in this single loop only, right? We are doing it in this single loop only. Cool. So now space complexity, obviously, we are using an extra space. We are saving all the nodes, so O of n. Cool. Great. Now, the interview might say, hey, I don't want you to use any extra space. You are using any extra space, that is fine, but I don't want you to do that. I want you to just find it in the using the linked list only. Cool, cool. We can do that. We can do that. Okay, let's make another list. I'm not going to use this because it won't be, because if you see that fast and slow pointer, if we use that approach again, it will be somewhere here. You will find it here only. Yeah, you would find it here only. Cool. Okay. Uh, you can obviously use a slow and fast pointer here, but no, you won't be. Sorry. So this is the naive approach. But let's jump onto the better slash optimal, right? Why optimal, right? Okay. Now, taking just a random example, 3, 2, 1, 6 minus 4 minus 3, 8, maybe a 7, 7, and 6 again, right? 6 again. Cool. Very random. Let's take slow here and fast here as well. And if you remember, we move slow by 1 pointer, fast by 2 points, right? We use this. We generally do this. Okay, let me save it somewhere here. This also goes here, right? Cool. Now slow and fast are here. Now slow moves by 1. Slow. Fast moves by 2. Cool. Slow moves by 1. Fast moves by 2. Slow moves again by 1. Fast moves by 2. Slow moves by 1. Fast again moves by 2. Slow moves by 1. Fast again moves by 2. This is the position that I have. So I have detected a cycle, right? Because my slow and fast are meeting. Had it been given that, hey, this is a linear, what do you call it? A linear linked list. So slow and fast would have been here. Slow would have moved by 1 and fast would have been 2 equal to null. So that means cycle is not present, right? But here we could find that, hey, cycle is present because slow and fast are meeting at the same point. That is why we can say that step 1 is done. That is detecting a loop. Okay. So we have detected the loop, right? We have detected the loop. But how can we say that what is the starting point, right? What is the starting point? Okay. What I can do is I can say that, hey, if at this point slow and fast are equal, what I'll do is I will move my slow back to head again. I will move my slow back to head again, right? So slow from here goes to this point, and my fast is at -3 only. Cool. Now I will move it by one step only. Only everything I'll just move it by one step. And I'm really sorry, I really missed this 7 here. I missed this 7 here, right? Um, okay, let's do one thing. So slow. Let's do one thing. Let's take some other example because I kind of missed that. I kind of missed that, right? Uh, or did I? Or did I? So I don't think fast will be here at all. Yeah, so I did not kind of, I obviously missed it, but I did not miss it on purpose. But to our luck, we already have a 7 in between, which was never visited by fast pointer. So okay, we can do that. Yeah, cool. Now let's move slow and fast by 1 points only, like 1 point. Let's move slow to this point. Fast moves to this point. Slow again moves to this point. Fast moves to this point. Slow moves to this point and fast again moves to this point. And this is the starting point, right? This is the starting point. So step 2, move slow to head and move slow and fast by 1 step. Slow equal to fast. This is the starting point. Cool. This is the starting point. Now we are sure that this is done. But how is it done, right? What is the proof behind it? Let's see. Let's see. Okay, cool. 3, 2, 1, 6 minus 4 minus 3, 8, 7. So 3, 2, 1. Let's kind of draw it again. 3, 2, 1, 6 minus 4. What was the other thing? Minus 3, 8, 7, right? Minus 3, 8, 7. And this 7 is joined to 6 back again. Cool. Cool. Let me ask you something. Let me ask you something. So slow was here and fast was here as well. Cool. If 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 slow is at this point, if slow is at this point, this is, let's just say, L1, right? This is length L, not L1. I should just take L, right? Where would my fast be? Now, fast will be at 2L, because if slow is moving by 1 step, then fast is moving by 2 steps. That means double of it. So 1, 2, 3, right? So 1, 2, 3, 4, 5, 6. Um, I'm really sorry. I'll have to do it again. So slow is here. So it moved 1, 2, 3 steps, right? So my fast will obviously move 6 steps. So 1, 2, 3, 4, 5, and 6. That means my fast will be somewhere here, correct? Let's say this is D. So my fast is D distances ahead. D distance ahead, right? If fast is D distance ahead, I'll have to find out. I'll have to find out. And let's see. Let's assume, where were they meeting? They were meeting at -3, right? They were meeting at -3. Now let me change the color. At this moment of time, my slow and fast meets again. My slow and fast meets again, right? So when we have done the cycle, so my slow and fast again are moving again. Cool. Let's find out what is this distance. What is this distance, right? Cool. 1, 2. Sorry, 1, 2, and 3, right? 1, 2, 3. 3 steps, 3 steps, right? So this is three steps. If I move slow to this point again and move slow by one step and fast also by one step to here, I am traversing three steps again and again, right? In the mathematics, you can say that, hey, distance is nothing but L plus D. So this is a bigger D. This is the bigger D, right? This is the bigger D because this whole cycle, this whole cycle, fast is moving twice of D. Now, why is it so? Because see, D right now, how much steps am I ahead of? See, let's assume that fast is approaching slow. Fast is approaching slow. Cool. My fast is at this point and my slow is at this point. So one and two. Let's say this is some distance, right? This is some distance S, right? This is some distance. Cool. If my, uh, if this is S, right? If this is S, then in the next step, fast will move by 2 points, slow will move by one step. Now my S becomes D minus one, and dot dot dot, this will eventually become zero. And why is it becoming zero? I've already explained to you in my previous video. Please go and check it out, right? So when it becomes zero, that means my fast has traveled 2D, right? 2D. That is two times the distance. That is this D. This D. This has traversed twice of this distance, right? And this is why it will travel another L to reach to this point. This is just take a pen and paper, just take a pen and paper and take any example. You don't have to get into the depth of, mathematics behind it. Just take a pen and paper, cyclic design any cyclic linked list, right? If you reach back to that step, taking L distance again, right? And L distance from head and L distance from where they are meeting. That means you are sure that, hey, this will always be moving to L distances, and that L is where my starting point of the cycle will be, right? Cool. What is the time complexity? Let's see. We discussed that, hey, O of N will be when, um, when this when slow and fast are moving. We discussed it when this detecting in the loop, right? If we detect a loop in the cycle, O of N is the time complexity. Again, another O of L, where this L is what? Distance of the starting point from head, right? Distance of starting of the loop from head is O of L. You can simply tell that in the interview. Space complexity, we are not using any extra space. We are not, right? Let's go and type down this code, right? I hope it was, I hope you understand. I know they detect basically when you have detected, that is fine. But how it moves only L distance, that you will have to take a pen and paper and then you will understand, right? Let's say that, hey, let slow is equals to head, fast is also at head. Let's take an entry point as well. Now I'll explain why I take an entry point, just not to move this slow back to the head. That is why I've took it. So while my fast is not equal to null, and fast dot next is also not equal to null, I will move slow is equal to slow dot next, fast is equal to fast dot next. If my slow is equal to fast, here I'll have to do something. But if this is not true, that means I'll have to return a null. If any of this or this thing, if this or this thing gets true, that means the cycle was not detected. It is a linear linked list. So that is why I'm returning null. But if slow n is equal to fast, I'll say that slow is equal to slow dot next. Entry is equal to entry dot next. If my slow is equal to entry, I have found my starting point. So I'll say return slow. Let's try to run this code. Okay, TLE, that means there is some problem. I'll have to run a loop, guys. While uh, slow is not equal to entry. I can say that, right? Cool. Because when we'll break out of the loop, this means we have it. So let's return this already. Oh, sorry, my fast is not moving by 2 points. That means I'll have to do something. I'll have to move it by 2 steps and not one. Accepted, right? Accepted. So fast moves by 2 points. While slow is not equal to entry, we'll move both by 1 steps. As soon as they are, I can also return entry because they will be at the same point. You don't have to worry. Let's try to submit this code. Great. Accepted, right? And why am I returning null here? Because I have found out that, hey, this is not a cyclic one. And that is what it is saying me, asking me to do. It is asking me to return the null. I hope you have understood this question. I know few people won't be able to understand, the proof of it. But let's do one thing. Let you should definitely write down any cyclic loop in your sorry, not cyclic loop, cyclic linked list in your on a pen on paper, and then you can discover that, hey, is it moving? Is it moving or not? Is it moving one step or not? Sorry, is it moving L steps or not? If they are not, come comment down on my video that, hey, your proof is wrong. I will definitely explain to you in a better manner, right? Thank you so much, guys, for joining in. I'll see you tomorrow. Okay, yeah, we can write some notes as well. I'm really sorry. So yeah, use slow and fast approach. As soon as you reach the meeting point, you can do you can take slow back to the head again, move slow and fast by 1 step, and you will notice that as soon as slow is equal to fast again, that means this is the starting point of the cycle. Let's save this and mark this as done. Yeah, flat. So yeah, what we can do is we can just take this question tomorrow, and then we'll start with linked lists and arrays, right? So thank you so much, guys, for joining in. I'll see you tomorrow with another video called flattening of a linked list. Thank you, guys. Bye bye.